Hello, and welcome to the Sleepy Astronomer. Tonight, you're gazing up at the same stars that have watched over Earth for billions of years, each one a distant nuclear furnace burning through the dark. Above you hangs a tapestry woven from the birth and death of countless suns, their light carrying stories of creation and destruction across the vast emptiness of space. Whether you're lying beneath a canopy of stars in the countryside, where the Milky Way spills across the darkness like cosmic dust, or perhaps settled indoors in a place where city lights have softened the night sky to just the brightest points of light, you're exactly where you need to be for tonight's journey through stellar time. If you're new to these gentle wanderings through the cosmos, welcome. If you've drifted with me before through other corners of the universe, thank you for returning. Tonight, we'll trace the complete biography of stars, from their first stirrings in the cold depths of nebulae to their final moments as they either fade away peacefully or explode in spectacular supernovae. We'll discover how these cosmic engines forge the very elements that make up your body, how ancient civilizations read stories in their patterns, and how their deaths seed the universe with the materials for new generations of stars and planets. We'll witness the gentle collapse of gas clouds that gives birth to new suns, follow a star through its billion-year journey of steady nuclear burning, and stand at the edge of stellar death, where the universe's most extreme objects are born. Along the way, we'll explore how every atom in your body except hydrogen was forged in the heart of a dying star, making you quite literally made of ancient starlight. So, settle in, let your breathing slow, and prepare to journey across billions of years of cosmic time, watching as stars are born, live their long lives, and ultimately give their substance back to the universe so that new stars, new worlds, and perhaps new life can begin again. The night sky has always been humanity's first book, written in points of light against the darkness. Long before we understood that stars were distant suns, our ancestors wove them into stories that helped to make sense of the world. The ancient Greeks saw heroes and monsters frozen in the constellations. The Aboriginal Australians read the Milky Way as the path spirits took to the afterlife. Polynesian navigators used the stars as their roadmap across vast ocean distances, reading the sky like we might read a GPS. But perhaps no culture was more captivated by the stars than the ancient Egyptians, who saw their most important deity, the sun god Ra, as a star that died each evening and was reborn each dawn. They understood, in their own way, something profound about stellar life cycles that we're only now beginning to fully appreciate. Every star does indeed die and contribute to the birth of something new. What those ancient observers couldn't have known is that they were looking at nuclear reactors scattered across space, each one converting hydrogen into helium and releasing the energy that makes them shine. They were witnessing a process so fundamental that without it, the universe would be a cold, dark, and lifeless place. No warmth, no light, no heavy elements to build planets and life. Just an endless expanse of hydrogen and helium drifting through the void. The stars you see tonight represent every stage of this cosmic story. Some are newborns, just beginning their long journey of nuclear fusion. Others are middle-aged, like our own sun, steadily burning through their stellar fuel. And some are ancient giants, nearing the end of their lives and preparing for the spectacular finale that will either see them fade quietly into the cosmic background or explode with the force of billions of nuclear weapons. Yet even in death, stars are generous. When a massive star ends its life in a supernova explosion, it doesn't just disappear. It enriches the surrounding space with heavy elements, the carbon, oxygen, silicon and iron that make rocky planets possible. It sends shock waves through nearby gas clouds, triggering the collapse that births new stars. In this way, stellar death becomes the seed of new stellar life, creating an endless cycle that has been running for over 13 billion years. This evening, as we drift together through the stages of stellar evolution, you might find yourself thinking about the incredible spans of time involved. While a human lifetime passes in decades, stars measure their lives in millions, billions, even trillions of years. A single star might shine steadily while entire species evolve, flourish, and go extinct on distant worlds. Mountains rise and crumble to dust. Continents drift across planetary surfaces, and still the star burns on. Yet for all their vast lifespans, stars do change. They grow, they age, they swell and shrink, and eventually they die. Understanding how they do this has been one of humanity's greatest intellectual achievements, requiring us to peer across impossible distances and decode the messages hidden in starlight itself. Tonight, we'll become cosmic archaeologists, reading the story of the universe in the light that reaches us from distant suns. We'll discover that the gentle twinkle of starlight carries within it the complete autobiography of each star, written in the specific colours of light they emit and the way that light changes over cosmic time. So as we begin this journey through stellar life and death, remember that you're not just observing the universe, you are part of it. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of these elements were created in the nuclear furnaces of stars that lived and died billions of years ago. You are, quite literally, the universe becoming aware of itself, contemplating its own cosmic story written in starlight. And with that thought warming us like stellar fire, let's begin our exploration by drifting toward the cold, dark nurseries where stars first begin to stir, where the universe's next generation of cosmic engines slowly take shape in the quiet depths of space. If you've ever looked up at the constellation Orion on a clear winter night, you might have noticed a fuzzy patch of light just below the 3 stars that form his belt. That soft glow, barely visible to the naked eye, is the Orion Nebula, and you're looking at one of the universe's stellar nurseries, in the very act of giving birth to new stars. At this moment, deep within those glowing clouds of gas and dust, gravity is slowly gathering material together, compressing it, heating it, until eventually nuclear fire ignites and a new star begins to shine. This process has been happening for over 13 billion years, yet it unfolds so slowly that even across human timescales, nebulae appear almost perfectly still. What seems like a static cloud frozen against the backdrop of space is actually a dynamic, ever-changing environment where the raw materials of the universe are being sculpted into the next generation of cosmic engines. The word nebula comes from the Latin word for cloud, and that's essentially what these stellar nurseries are. Vast clouds of hydrogen gas mixed with tiny grains of dust, spread across regions of space so enormous that light takes years to cross from one side to the other. To put that in perspective, imagine a cloud so large that if you could travel at the speed of light, it would take you longer to cross it than the entire recorded history of human civilization. Yet for all their immense size, nebulae are remarkably tenuous. The gas within them is so thin that it makes the best vacuum we can create on Earth seem dense by comparison. If you could somehow stand inside a nebula, you might not even realize you were there. The gas would be so diffuse that each cubic centimeter would contain only a few hundred atoms, compared to the trillions upon trillions in each breath you take. But given enough time, even this incredibly thin material can come together under the patient pull of gravity. It starts with the smallest of fluctuations, perhaps a slightly denser region, where the gas is just a little more concentrated than its surroundings. Gravity, though weak, begins to tug at nearby material, drawing it in. As more matter accumulates, the gravitational pull grows stronger, attracting even more material in a slow but inexorable process that can take millions of years. Ancient cultures looked up at these fuzzy patches of light with wonder and imagination. The Aboriginal Australians saw the dark lanes that run through the Milky Way as the emu in the sky, a cosmic bird whose body was outlined by the dust clouds that block the light from stars beyond. Native American tribes told stories of these celestial clouds as the breath of their ancestors, or as cosmic campfires around which the spirits of the dead would gather. The ancient Chinese astronomers were particularly attentive to what they called guest stars, new points of light that would occasionally appear in familiar constellations. What they were sometimes witnessing were the birth announcements of new stars, the moment when a collapsing cloud finally ignited nuclear fusion and began to shine for the first time. They couldn't have known they were watching the universe's most fundamental process of creation, the transformation of simple hydrogen gas into the complex nuclear reactors that power cosmic evolution. As a cloud of gas begins to collapse under its own gravity, several beautiful things start to happen. First, the cloud begins to spin, just as an ice skater spins faster when they pull their arms in close to their body. The collapsing cloud accelerates its rotation as it contracts. This spin will eventually determine many aspects of the star system that forms, creating the flattened disk of material from which planets might one day condense. Second, the cloud begins to fragment. Rather than collapsing into a single massive object, gravitational instabilities cause it to break apart into smaller, denser cores. This is why stars are often born not alone, but in clusters containing dozens or even hundreds of sibling stars, all formed from the same parent cloud and sharing a common origin story written in their chemical composition and motion through space. As each fragment continues to collapse, the material at its center becomes increasingly compressed. With compression comes heat, and slowly, over millions of years, the core of the collapsing cloud begins to warm up. At first, it glows only in infrared light, invisible to our eyes but detectable by specialized telescopes. These warm dust cocoons are some of the youngest objects in the universe, protostars in the very earliest stages of their formation. The temperature and pressure at the core continue to rise as more and more material rains down from the surrounding cloud. When the core temperature reaches about 10 million degrees Celsius, something remarkable happens. The hydrogen nuclei, which have been bouncing around individually, begin to overcome their natural repulsion and fuse together. Two hydrogen nuclei combine to form a single helium nucleus, releasing a tremendous amount of energy in the process. This is the moment of stellar birth when a protostar becomes a true star. The nuclear fusion in its core begins producing enough energy to halt the gravitational collapse, creating a delicate balance between the inward pull of gravity and the outward pressure of radiation. The star has reached what astronomers call hydrostatic equilibrium, the stable condition that will define most of its life. The newly ignited star announces its arrival by blowing away the remaining gas and dust that surrounds it. Strong stellar winds, powered by the energy of nuclear fusion, sweep the birth material out into space, revealing the bright young star within. Sometimes this process creates beautiful structures like the pillars of creation in the Eagle Nebula, where the intense radiation from newly formed stars sculpts the surrounding gas into towering columns and delicate wisps. But not all stellar births are identical. The mass of the original collapsing core determines what kind of star will emerge. If the core contains less than about 8% of our Sun's mass, it will never become hot enough to ignite hydrogen fusion. Instead, it will become a brown dwarf, a failed star that glows dimly from the heat of its formation, but never achieves the nuclear fire that defines true stellar life. On the other end of the spectrum, if the core is extremely massive, more than about 100 times the mass of our Sun, the resulting star will be so luminous and hot that its own radiation pressure will blow away much of its outer layers, preventing it from growing even larger. These stellar giants burn so ferociously that they consume their nuclear fuel in just a few million years, living fast and dying young in spectacular explosions. Most stars, including our own Sun, fall somewhere in the middle of this range. They form with enough mass to sustain nuclear fusion for billions of years, but not so much that they burn out quickly. These are the stars that provide the stable, long-term energy sources that make the development of complex chemistry, and perhaps even life, possible. The stellar nurseries where these births take place are among the most beautiful objects in the cosmos. The gas glows in brilliant colours as it's excited by the ultraviolet light from nearby young stars. Hydrogen glows red, oxygen shines blue-green, and sulfur emits a subtle golden light. The result is a cosmic palette that creates some of the most stunning images in astronomy, from the rose-coloured petals of the Rosette Nebula to the intricate structures of the Crab Nebula. Yet even as we marvel at their beauty, these nebulae remind us of the cosmic recycling that makes stellar birth possible. The gas and dust in these clouds aren't pristine material left over from the Big Bang. Much of it has been processed through previous generations of stars, enriched with heavier elements forged in stellar cores, and scattered into space when those ancient stars died. The carbon, oxygen, and other elements mixed into the hydrogen provide the seeds from which rocky planets and complex molecules can eventually form. This means that every star born today is, in a sense, a second or third generation star, inheriting the chemical legacy of the stars that came before. Our own Sun formed about 4.6 billion years ago from a cloud that had been enriched by countless previous stellar generations, which is why the Earth that condensed from the leftover material contained the heavy elements necessary for geology, oceans, and eventually life. The process of stellar birth also creates the conditions for planetary formation. As the young star settles into its stable nuclear burning phase, the leftover disk of gas and dust begins its own process of aggregation. Tiny dust grains stick together to form pebbles. Pebbles collide to create rocks, and rocks accumulate into asteroids. Given enough time and material, some of these growing bodies will become planets, carrying forward the story that began with the gentle collapse of a gas cloud millions of years earlier. Standing back and contemplating this process, there's something profoundly moving about stellar birth. In the cold depths of space, with no intervention, no guiding hand, no conscious intent, gravity slowly shapes diffuse gas into nuclear reactors that will burn for billions of years. It's a reminder that complexity and beauty can emerge from the simplest physical laws, given enough time and space to work. The ancient Polynesian navigators, crossing vast ocean distances guided only by the stars, understood something profound about these lights in the sky. They saw them not as static decorations, but as dynamic guides that changed position throughout the night and across the seasons. In their own way, they recognized that the cosmos is not a fixed tableau, but an ever-changing story of which they were a part. Tonight, as you look up at the stars, Remember that scattered among those points of light are stellar nurseries, where this ancient process continues. In the Eagle Nebula, in the Orion Complex, in countless other star-forming regions across our galaxy, gravity is patiently gathering gas and dust, compressing it, heating it, preparing to ignite new nuclear fires that will burn long after our own species has passed into cosmic history. And with that thought of new stars slowly stirring to life in the cold depth of space, we turn our attention to what happens next in their cosmic story. For once a star achieves the delicate balance of nuclear fusion, it enters the longest phase of its existence, a period of steady burning that astronomers call the main sequence, where it will spend most of its stellar lifetime converting hydrogen into helium and shining steadily into the cosmic night. Our own sun has been burning steadily for about 4.5 billion years, and it will continue this patient work for another 5 billion years or so. During all that time, it maintains an almost perfect balance, like a cosmic thermostat that automatically adjusts to keep conditions stable. This is the main sequence phase of stellar life, and it represents the vast majority of any star's existence. A long, peaceful period of nuclear burning that provides the steady energy output that makes planets habitable and life possible. The name main sequence comes from early 20th century astronomers who plotted stars on a graph comparing their brightness to their colour. When they did this, they discovered that most stars fell along a diagonal line on the graph, with hot blue stars being very bright and cool red stars being quite dim. This diagonal band became known as the main sequence, and we now understand it represents stars in their prime, steadily fusing hydrogen in their cores. To understand what's happening inside a main sequence star like our Sun, imagine a sphere of gas so massive that its own gravity creates pressures and temperatures beyond anything we can replicate on Earth. At the very centre, where the pressure is greatest, hydrogen nuclei are moving so fast and colliding so frequently that they overcome their natural tendency to repel each other. When 4 hydrogen nuclei manage to fuse together, they create one helium nucleus, but with slightly less mass than the original 4 hydrogen atoms. That tiny bit of missing mass doesn't just disappear. According to Einstein's famous equation E=mc², it gets converted into pure energy. And because the speed of light squared is an enormous number, even a small amount of mass produces a tremendous amount of energy. Every second, our Sun converts about 600 million tons of hydrogen into helium, and in the process, it radiates energy equivalent to trillions of nuclear bombs. Yet for all this violent nuclear activity happening in its core, the Sun's surface remains remarkably stable. The energy produced by fusion works its way slowly outward, taking somewhere between 100,000 and 1,000,000 years to make the journey from the core to the surface. By the time it emerges as sunlight, that energy has been scattered, absorbed, and re-emitted countless times, transformed from the high-energy gamma rays of nuclear fusion into the gentler visible light that warms your face on a sunny day. This process of nuclear fusion doesn't just power the star, it also creates new elements. When 4 hydrogen nuclei fuse to form helium, you're witnessing the universe's primary method of element creation. Every helium nucleus in your body, every helium atom that makes a balloon float, was forged in the core of a star during its main sequence lifetime. In this way, stars serve as cosmic alchemists, transforming the universe's primordial hydrogen into more complex elements. Ancient civilizations recognized something special about the steadiness of stellar light. Egyptian astronomers noticed that certain stars rose at the same time each year, marking the seasons with clockwork precision. The star Sirius, which they called Sopdet, announced the annual flooding of the Nile River with such reliability that it became central to their calendar system. They couldn't have known they were observing the steady nuclear burning of a main sequence star, but they understood intuitively that this consistency was something they could depend upon. The Hindu concept of cosmic time includes vast cycles called kalpas, periods so long that they stretch across billions of years. In their cosmology, the universe breathes in cycles of creation and destruction that span these enormous timescales. Modern astronomy has revealed that they weren't far off. The main sequence lifetimes of stars do indeed unfold across these cosmic time periods, with the most massive stars burning for millions of years and the smallest potentially glowing for trillions. The length of a star's main sequence lifetime depends entirely on its mass, but in a counterintuitive way. You might think that a more massive star with more fuel to burn would live longer, but the opposite is true. Massive stars burn their hydrogen fuel so ferociously that they consume it much faster than their smaller cousins. A star 10 times more massive than our Sun will live for only about 20 million years, while a star half the Sun's mass will burn steadily for 20 billion years, longer than the universe has currently existed. This relationship between mass and lifetime creates an interesting hierarchy in stellar neighborhoods. The most massive, brightest stars are like cosmic lighthouses, illuminating vast regions of space with their intense radiation. But they're also the short-lived members of their stellar generation, burning out while their smaller, dimmer siblings are still in their stellar youth. It's as if the universe has a trade-off built into its stellar economy. You can burn bright, or you can burn long, but you can't do both. During their main sequence years, stars like our Sun are remarkably stable. The nuclear furnace in the core produces just enough energy to balance the inward pull of gravity, creating what astronomers call hydrostatic equilibrium. It's a delicate dance between competing forces. If fusion slows down even slightly, gravity begins to compress the core, which raises the temperature and speeds up fusion until the balance is restored. If fusion speeds up too much, the core expands and cools until the reaction rate drops back down. This stellar thermostat is so sensitive that our Sun's energy output has varied by less than 0.1% over the entire period that we've been able to measure it accurately. That stability has been crucial for life on Earth, providing the steady warmth that has allowed our planet's climate to remain hospitable for billions of years. Without the reliable nuclear burning of a main sequence star, the complex chemistry of life would never have had time to develop. But even during this stable phase, stars are slowly changing. As hydrogen in the core gets converted to helium, the composition of the stellar interior gradually shifts. Helium nuclei are more massive than hydrogen nuclei, so the core becomes slightly denser over time. This slow change in the star's internal structure causes its surface temperature and brightness to change very gradually, so slowly that the difference is imperceptible on human timescales, but measurable over hundreds of millions of years. Our Sun today is about 30% brighter than it was when it first settled onto the main sequence 4.5 billion years ago. This gradual brightening is one of the challenges that planetary climates must navigate over geological time. Earth has managed to maintain relatively stable temperatures despite this changing stellar output through a complex interplay of atmospheric chemistry, ocean circulation, and the carbon cycle. It's a reminder that even the most stable-seeming cosmic processes are actually dynamic when viewed across appropriate timescales. The nuclear fusion happening in stellar cores creates more than just helium. In the hottest, most massive stars, the temperatures and pressures are sufficient to forge elements up to iron in the periodic table. Carbon, nitrogen, oxygen, silicon, all of these elements can be created through various fusion processes during a star's main sequence lifetime, though most of this element creation happens later in the star's evolution. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of these elements were created through nuclear fusion in stellar cores. When Carl Sagan famously said, "We are made of star stuff," he was referring to this process of stellar nucleosynthesis. Every atom in your body heavier than hydrogen and helium was forged in the nuclear furnace of a star, either during its main sequence lifetime or in the dramatic events that mark stellar death. Different types of stars contribute different elements to the cosmic inventory. Low-mass stars like our Sun primarily create helium during their main sequence years, with small amounts of carbon and nitrogen produced through secondary fusion processes. More massive stars can create oxygen, silicon, and sulfur. The very largest stars produce elements all the way up to iron, creating the full range of materials needed for rocky planets and complex chemistry. This element creation happens incredibly slowly by human standards. It takes millions or billions of years for a star to significantly change the composition of its core through fusion. Yet when viewed across cosmic time, stellar nucleosynthesis has gradually enriched the universe, increasing the abundance of heavy elements with each generation of stars. The early universe contained only hydrogen and helium, but billions of years of stellar alchemy have created the rich chemical diversity we see today. Ancient Greek philosophers like Empedocles proposed that everything was made from four fundamental elements: earth, air, fire, and water. They couldn't have imagined that the real elements were being created in stellar furnaces through processes involving temperatures of millions of degrees and pressures beyond earthly experience. Yet in a poetic sense, they weren't entirely wrong. The fire of nuclear fusion really is what creates the materials from which everything else is built. The steadiness of main sequence burning has philosophical implications that stretch beyond astronomy. In a universe that often seems chaotic and unpredictable, stars provide an example of long-term stability emerging from dynamic processes. The nuclear reactions in a stellar core are individually violent and random, yet collectively they create a smooth, steady output that can persist for billions of years. This stellar constancy has been crucial for the development of complex structures in the universe. Planets need billions of years to develop interesting geology. Life requires eons to evolve from simple chemistry into complex organisms. Civilizations need stable energy sources to develop technology and explore their cosmic surroundings. The patient nuclear burning of main sequence stars provides the temporal foundation upon which all of these developments can occur. As you look up at the stars tonight, most of what you're seeing represents this stable phase of stellar life. The bright stars of familiar constellations, the countless dimmer points of light that fill the spaces between them. These are primarily main sequence stars going about their quiet work of nuclear fusion, converting hydrogen to helium and radiating energy into the cosmic night. But this stable phase doesn't last forever. Eventually, even the most patient star begins to run low on hydrogen fuel in its core. When that happens, the delicate balance between gravity and radiation pressure starts to shift, and the star begins its journey toward the dramatic changes of old age. The steady burn of the main sequence gives way to the swelling and brightening of stellar maturity as stars enter their giant phase and begin the complex processes that will ultimately determine their final fate. And it's to these aging giants with their swollen atmospheres and increasingly unstable nuclear burning that we turn our attention next, exploring how stars begin their transformation from steady, reliable fusion reactors into the unpredictable and magnificent objects that mark the beginning of stellar old age. When our Sun has burned through most of the hydrogen in its core, about 5 billion years from now, it will begin one of the most dramatic transformations in stellar evolution. The steady, reliable burning that has warmed Earth for eons will give way to an increasingly unstable phase of stellar life, as our star swells to enormous size and begins its journey toward whatever final fate awaits it in the cosmic future. This transformation from main sequence star to red giant represents one of the most profound changes a star can undergo while still maintaining nuclear fusion in its interior. It's a process that plays out over millions of years, yet results in changes so dramatic that the star becomes almost unrecognizable from its former self. The story begins when a star starts to run low on hydrogen fuel in its core. For billions of years, the core has been the site of steady nuclear fusion, converting hydrogen into helium and maintaining the delicate balance between gravitational collapse and radiation pressure. But as more and more hydrogen gets consumed, the core begins to fill up with helium, the ash of nuclear burning. Helium nuclei are much more difficult to fuse than hydrogen nuclei. They have twice the electric charge, which means they repel each other much more strongly. To overcome this repulsion and force helium nuclei to fuse together requires temperatures of about 100 million degrees Celsius, roughly 10 times hotter than the conditions needed for hydrogen fusion. Most stars simply aren't massive enough to achieve these extreme temperatures in their cores. So what happens when the hydrogen runs out? The nuclear fires in the core begin to dim, and without the outward pressure of radiation to balance gravity's inward pull, the core starts to contract. This contraction raises the temperature and density in the regions just outside the core, where there's still some hydrogen left to burn. Soon, nuclear fusion ignites in this shell around the now dormant core, creating what astronomers call shell burning. Shell burning is much more unstable than the steady core fusion that powered the star during its main sequence lifetime. The fusion reactions in the shell are more sensitive to changes in temperature and pressure, leading to fluctuations in energy output. Sometimes the shell burns vigorously, sometimes it dims, creating a kind of stellar breathing that can cause the star's brightness to vary over timescales of years or decades. But the most dramatic change is what happens to the star's outer layers. The energy from shell burning causes the star's atmosphere to expand enormously. A star like our Sun, currently about 1.4 million kilometers in diameter, will swell to nearly the size of Earth's orbit, roughly 300 million kilometers across. If you could somehow survive the transformation, you would watch our Sun grow from a bright point of light to a vast glowing sphere that fills most of the sky. This expansion causes the star's surface temperature to drop significantly. While the Sun's surface currently glows at about 5,500 degrees Celsius, giving it a yellowish color. As a red giant, it will cool to perhaps 3,000 degrees, causing it to glow with a deep red or orange hue. The star becomes what we call a red giant, cooler on the surface but much larger and often more luminous overall than it was during its main sequence years. Ancient astronomers were familiar with stars that seem to change in brightness over time. The star Mira, whose name means wonderful in Latin, was noticed by early observers because it would brighten and dim in a regular cycle lasting about 11 months. We now know that Mira is a red giant star undergoing the kind of shell burning that makes these evolved stars variable in brightness. For ancient cultures, such changing stars were often seen as omens or messages from the gods. The Chinese astronomers kept particularly detailed records of stellar variations, noting when familiar stars grew brighter or dimmer, or when new stars appeared where none had been visible before. In their cosmology, the heavens were supposed to be unchanging and eternal, so variations in stellar brightness were considered significant events that might foretell changes in the earthly realm. They couldn't have known they were observing the natural aging process of stars, the stellar equivalent of watching an elderly person's hair grow grey. Celtic mythology often spoke of the fires of old age, referring to the way elderly people sometimes seem to burn with a different kind of intensity than they had in their youth. In a poetic sense, red giant stars embody this same concept. They are stellar elders that burn with a different, often brighter flame than they did in their youth, but with an underlying instability that speaks of approaching change. During their red giant phase, stars begin to lose mass at an accelerated rate. The expanded outer atmosphere is only loosely bound by the star's gravity, and stellar winds carry material away into space at rates thousands of times higher than during the main sequence phase. Our Sun currently loses about 1 Earth mass worth of material every 150 million years through its solar wind. As a red giant, it will lose mass at a rate more than 1,000 times faster. This mass loss creates beautiful structures in the space around aging stars. The expelled material forms expanding shells of gas that glow when illuminated by the star's radiation. These structures, called planetary nebulae despite having nothing to do with planets, are among the most visually striking objects in the night sky. The Ring Nebula in the constellation Lyra, the Helix Nebula in Aquarius, and the Cat's Eye Nebula in Draco are all examples of the gorgeous aftermath of red giant mass loss. The chemical composition of this expelled material tells an important story about stellar evolution. During its main sequence lifetime, the star has been steadily converting hydrogen to helium in its core. Now, as convection currents in the expanded envelope bring material from the interior to the surface, the star begins to reveal the products of its nuclear alchemy. Elements created through fusion processes, carbon, nitrogen, oxygen, are mixed into the outer layers and then carried away by stellar winds. This process, called dredge-up, is one of the ways that stars enrich the interstellar medium with heavy elements. When you breathe out carbon dioxide, you're exhaling carbon atoms that were quite possibly created in the core of a red giant star billions of years ago, then expelled into space through stellar winds, incorporated into a gas cloud, and eventually condensed into the rocky materials that became Earth and all life upon it. Red giant stars also become sites of more exotic nuclear processes. While the core remains dormant, unable to fuse helium at the relatively low temperatures achieved through gravitational contraction, the shell burning around the core can create conditions suitable for more complex fusion reactions. Some red giants become what are called asymptotic giant branch stars, undergoing periodic episodes of enhanced burning that can create elements like fluorine, neon, and even heavier elements through neutron capture processes. The instability of red giant burning creates another interesting phenomenon: stellar pulsations. Some red giants expand and contract rhythmically, like cosmic heartbeats that can be detected through careful measurements of their brightness and colour. These pulsations are driven by changes in the opacity of the star's outer layers as they heat up and cool down, creating a kind of valve mechanism that regulates the flow of energy from the interior. The most famous of these pulsating red giants is the star Betelgeuse in the constellation Orion. This massive red supergiant is so large that if it replaced our Sun, its surface would extend beyond the orbit of Mars. Betelgeuse varies in brightness over periods of months and years, and its enormous size and proximity to Earth, only about 650 light-years away, make it one of the few stars whose surface features can actually be resolved by our most powerful telescopes. Ancient Arabic astronomers name this star Yad al-Jawza, meaning the Hand of Orion, though the name evolved through various translations into the modern Betelgeuse. They recognized it as one of the brightest and most distinctive stars in the winter sky, not knowing that they were looking at a stellar giant in its final evolutionary phases, a star that has already left the main sequence behind and is approaching the end of its nuclear-burning lifetime. The red giant phase represents a crucial transition in stellar evolution. For lower-mass stars like our Sun, it marks the beginning of the end, the start of a process that will eventually lead to the complete cessation of nuclear fusion and the star's transformation into a white dwarf. For more massive stars, the red giant phase is just one step in a more complex evolutionary sequence that will involve multiple phases of nuclear burning and ultimately culminate in explosive stellar death. During this phase, the star is essentially buying time, with the core no longer able to sustain hydrogen fusion and not yet hot enough for helium burning. Shell fusion provides a temporary solution that allows the star to continue shining for millions of years while its core slowly contracts and heats up. It's a period of stellar middle age, when the star is no longer young and stable, but not yet ready for its final transformation. For planets orbiting red giant stars, this phase brings dramatic changes. As our Sun expands, Earth's orbit will be bathed in intense heat and radiation. The oceans will boil away, the atmosphere will be stripped off into space, and our planet will be transformed from a living world into a scorched, airless rock. The habitable zone around the star will move outward, potentially making the moons of Jupiter and Saturn temporarily warm enough for liquid water, though these conditions will last only a few million years before the star continues its evolution toward its final fate. Red giants remind us that even the most stable, long-lived objects in the universe are ultimately temporary. The sun that has shone steadily for billions of years, providing the energy that powers all life on Earth, will someday enter this unstable phase of swelling and brightening before beginning its final fade towards stellar death. It's a reminder of the deep timescales on which cosmic evolution operates, and of our place within that vast temporal landscape. Yet there's also something hopeful about the red giant phase. As these aging stars lose mass and enrich the surrounding space with heavy elements, they're contributing to the cosmic recycling that makes new generations of stars and planets possible. The death of old stars provides the raw materials for stellar birth, ensuring that even as individual stars age and die, the universe continues to create new sites for complexity, chemistry, and perhaps even life. As we contemplate these swollen, aging giants slowly losing their grip on their outer layers, we begin to approach one of the most dramatic moments in stellar evolution. For most stars, the red giant phase eventually leads to a quiet fade into stellar retirement. But for the most massive stars, something far more spectacular awaits. A final explosion so violent that it can briefly outshine an entire galaxy, forging the heaviest elements in the universe and seeding space with the materials needed for the next generation of cosmic evolution. In the year 1054 CE, Chinese astronomers recorded the appearance of a guest star in the constellation Taurus, so bright that it could be seen during daylight for nearly a month. Native American petroglyphs from the same period may preserve artistic records of this celestial visitor, showing a bright star near a crescent moon in the exact configuration that would have been visible from North America at that time. What these ancient observers witnessed was the death of a massive star, a supernova explosion that occurred about 6,500 years ago, with its light only just reaching Earth in the 11th century. Today we can see the aftermath of that stellar death. The Crab Nebula, an expanding cloud of glowing gas about 6 light-years across, marks the spot where that ancient star ended its life in one of the most powerful explosions the universe can produce. At the center of the nebula lies a neutron star, spinning 30 times per second and emitting beams of radiation like a cosmic lighthouse, the compressed remnant of what was once a star perhaps 20 times more massive than our Sun. This is the fate that awaits the most massive stars in the universe. While stars like our Sun will end their lives relatively quietly, gradually puffing off their outer layers to become white dwarfs, the stellar giants follow a very different path toward extinction. Their deaths are among the most energetic events in the cosmos, explosions so powerful that they can be seen from billions of light-years away and briefly outshine entire galaxies containing hundreds of billions of stars. The journey towards supernova begins when a massive star, typically more than 8 times the mass of our Sun, exhausts the hydrogen fuel in its core and begins the process of successive nuclear burning phases. Unlike lower mass stars, which lack the gravitational pressure to ignite helium fusion, massive stars have cores hot and dense enough to burn increasingly heavy elements in a series of nested shells, like a cosmic onion with different fusion reactions happening at different depths. First, helium nuclei fuse together to create carbon and oxygen. When the helium runs out, carbon begins to burn, creating neon, sodium, and magnesium. Neon burning follows, producing oxygen and magnesium. Then, oxygen burning creates silicon, sulfur, and other elements around the middle of the periodic table. Finally, silicon burning produces iron, nickel, and cobalt, elements that cluster around iron in the periodic table. Each of these burning phases becomes progressively shorter and more unstable. A massive star might spend millions of years burning hydrogen, thousands of years burning helium, hundreds of years burning carbon, and just a few years burning silicon. The final phase of silicon burning, which creates iron in the star's core, might last only a few days. It's as if the star is rushing headlong toward its final moment, burning through its nuclear fuel with increasing desperation. Iron represents a crucial turning point in stellar nucleosynthesis. All the fusion reactions that produce elements lighter than iron actually release energy. This is what powers the star and creates the outward pressure that balances gravity's inward pull. But fusion reactions that would create elements heavier than iron actually require energy input rather than producing it. When a massive star's core becomes dominated by iron, the nuclear furnace that has sustained it for millions of years suddenly shuts off. The transition between these burn-in phases becomes increasingly rapid as the star ages. While hydrogen burning might sustain a massive star for 10 million years, helium burning lasts perhaps 1 million years. Carbon burning occurs over a few thousand years. Neon burning over just a few years. And oxygen burning might last only months. Silicon burning, the final phase that creates iron, happens so quickly that it's measured in days or even hours. It's as if the star is falling down a staircase, each step shorter than the last, accelerating toward its inevitable conclusion. During these final burning phases, the star develops a complex internal structure resembling the layers of an onion. At the center lies the growing iron core, surrounded by a shell where silicon is burning to create more iron. Outside that, oxygen burns to create silicon and sulfur. Beyond that, neon burning produces oxygen and magnesium, while carbon burning creates neon and sodium in the outer shells. Each layer burns at its own temperature and rate, creating a delicate and unstable architecture that cannot persist for long. Without the outward pressure from nuclear fusion, gravity wins decisively. The iron core, roughly the size of Earth but containing more mass than our Sun, begins to collapse catastrophically. In less than a second, the core shrinks from thousands of kilometers across to perhaps 20 kilometers in diameter. The protons and electrons in the iron nuclei are crushed together to form neutrons, releasing a tremendous burst of neutrinos, ghostly particles that normally interact so weakly with matter that they can pass through the entire Earth without hitting a single atom. These neutrinos carry away an enormous amount of energy from the collapsing core. In fact, about 99% of the energy released during core collapse escapes in the form of neutrinos, with only 1% going into the visible explosion. Trillions upon trillions of these particles stream outward from the dying star at nearly the speed of light. When Supernova 1987A exploded in a nearby galaxy, neutrino detectors deep underground on Earth registered the arrival of these ghostly messengers about 3 hours before the light from the explosion became visible, providing the first direct evidence of the core collapse process that drives supernova explosions. The collapse happens so quickly that the outer layers of the star don't have time to follow. When the core bounces back from its ultra-compressed state, it sends a shock wave racing outward through the star at thousands of kilometers per second. This shock wave, powered by the enormous energy of core collapse and the neutrinos streaming out from the newly formed neutron star, blows the outer layers of the star apart in the explosion we call a supernova. Ancient cultures developed various explanations for the sudden appearance of bright new stars. Some Norse traditions spoke of the death of gods creating new lights in the sky, while certain Aboriginal Australian stories describe bright new stars as the souls of great warriors ascending to join their ancestors. In Hindu cosmology, the periodic appearance of exceptionally bright stars was sometimes interpreted as marking the end of one cosmic age and the beginning of another. The ancient Mayan astronomers, with their sophisticated understanding of celestial cycles, track the appearances of what they called new fire stars with remarkable precision. They understood that these events followed patterns over very long timescales, though they interpreted them through the lens of their cyclical view of cosmic history. In their cosmology, the universe itself went through periods of creation and destruction, and the appearance of brilliant new stars was sometimes seen as reflecting these larger cosmic rhythms. Japanese historical records from the Heian period describe the 1181 supernova in the constellation Cassiopeia, which was visible for 185 days and noted for its changing colour as it faded. Court astronomers interpreted this as a celestial event of great significance, possibly foretelling changes in the imperial succession. They couldn't have known they were observing the death throes of a star 20 times more massive than the Sun, located over 8,000 light-years from Earth. These intuitive connections between stellar death and cosmic renewal turn out to be more scientifically accurate than ancient peoples could have imagined. Supernovae are indeed agents of cosmic renewal, but not because they mark arbitrary temporal boundaries. Rather, they serve as the universe's primary mechanism for creating and distributing the heaviest elements, the materials essential for rocky planets, complex chemistry, and life as we know it. The aftermath of a supernova explosion continues to influence its cosmic neighborhood for thousands of years after the initial blast. The expanding shockwave creates what astronomers call a supernova remnant, a glowing shell of hot gas that can stretch across dozens of light years. These remnants are not just beautiful, they serve as cosmic laboratories where extreme physics creates conditions unlike anything we can reproduce on Earth. As the shockwave ploughs through the interstellar medium, it compresses and heats the surrounding gas to temperatures of millions of degrees. This process accelerates particles to enormous energies, creating cosmic rays that travel throughout the galaxy at nearly the speed of light. Some of these high-energy particles eventually strike Earth's atmosphere, where they create cascades of secondary particles that rain down on the planet's surface. In a very real sense, every person on Earth is constantly being bombarded by the energetic remnants of stellar explosions that occurred thousands of years ago. The Vela supernova remnant, visible in the southern sky, represents the aftermath of a stellar explosion that occurred roughly 11,000 years ago. The shockwave from this explosion is still expanding, now stretching across about 100 light-years of space. Aboriginal Australian cultures in the southern hemisphere may have witnessed this explosion, as some of their oral traditions speak of a great fire star that appeared in the sky during the dream time, bright enough to cast shadows at night. During the few seconds of core collapse and explosion, conditions inside the dying star become extreme enough to forge elements that cannot be created by any other known process. The intense neutron flux created during the explosion drives rapid neutron capture processes, where atomic nuclei absorb neutrons faster than they can decay. This creates a pathway to elements heavier than iron, including gold, platinum, uranium, and many others that exist only because of supernova nucleosynthesis. The gold in your jewelry, the silver in your electronics, the uranium that powers nuclear reactors, all of these elements were created during the final seconds of massive stars' lives, in explosions so violent that they temporarily recreate conditions similar to those that existed in the first moments after the Big Bang. When Carl Sagan spoke of humans being made of star stuff, he was referring not just to the carbon and oxygen created during normal stellar burning, but to these exotic heavy elements that can only be forged in the crucible of stellar death. The explosion doesn't just create heavy elements, it also distributes them throughout the galaxy. The shockwave from a supernova can travel at speeds of 10,000 kilometers per second or more, carrying the newly created elements far from their stellar birthplace. As this expanding shell of hot gas encounters the interstellar medium, it creates a supernova remnant, a glowing bubble of enriched material that can remain visible for thousands of years. These supernova remnants serve as cosmic recycling centers, mixing the products of stellar nucleosynthesis with the surrounding interstellar gas and dust. Over time, this enriched material becomes available for incorporation into new stars and planetary systems. The Sun and all the planets in our solar system formed from material that had been processed through multiple generations of stellar evolution, including the supernova explosions that created many of the heavy elements we find on Earth. The energy released by a supernova is almost incomprehensible in human terms. In the span of a few seconds, a single exploding star can release more energy than our Sun will produce over its entire 10 billion year lifetime. If a supernova occurred at the distance of our nearest stellar neighbour, Proxima Centauri, it would appear about as bright as the Sun in our sky and would deliver enough radiation to severely damage Earth's ozone layer and disrupt the planet's climate for years. Fortunately, there are no supernova candidates close enough to Earth to pose such a threat. The nearest massive star that might explode as a supernova is Betelgeuse, about 650 light-years away. far enough that its eventual explosion will provide a spectacular light show without causing serious damage to our planet. When Betelgeuse does explode, perhaps sometime in the next 100,000 years, it will likely become bright enough to cast shadows at night and remain visible during the day for weeks or months. Different types of massive stars produce different kinds of supernovae, depending on their mass, composition, and evolutionary history. The most massive stars, with initial masses perhaps 40 times that of our Sun, may undergo such violent core collapse that they form black holes directly, with little or no visible explosion. These failed supernovae represent stellar deaths so complete that the entire star simply vanishes from view, leaving behind only a black hole and perhaps a brief burst of neutrinos as evidence of the catastrophe. Stars of intermediate mass, roughly 8 to 25 solar masses, typically produce the classic supernova explosions that ancient astronomers observed and that modern telescopes detect in distant galaxies. These explosions leave behind neutron stars, objects so dense that a teaspoonful of neutron star material would weigh about as much as Mount Everest. Some of these neutron stars become pulsars, spinning rapidly and emitting beams of radiation that sweep across space like cosmic lighthouses. The supernova process also creates and accelerates cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. These cosmic rays, many of them protons and heavier atomic nuclei accelerated in supernova shockwaves, provide another mechanism for mixing stellar processed material throughout the galaxy. When cosmic rays strike gas clouds in the interstellar medium, they can trigger chemical reactions that create new molecules, including some of the organic compounds that serve as building blocks for more complex chemistry. There's something profoundly moving about the way stellar death becomes the foundation for new cosmic complexity. The violence of supernova explosions might seem purely destructive, but they serve essential creative functions in cosmic evolution. They create elements that cannot be made any other way. They distribute these elements throughout galaxies. They compress nearby gas clouds, sometimes triggering the formation of new stars. They inject energy into the interstellar medium, driving galactic-scale circulation patterns that help regulate star formation rates. In ancient Egyptian mythology, the god Osiris was said to die and be reborn, his death and resurrection symbolizing the eternal cycles of renewal that govern all existence. Modern astrophysics has revealed that stellar death and rebirth represent a literal truth about cosmic evolution. The death of massive stars truly does enable the birth of new stellar generations, in an endless cycle that has been operating for over 13 billion years. As we contemplate the awesome power of stellar death, we begin to understand how even the most extreme cosmic violence can serve creative purposes in the universal scheme. The same explosions that mark the end of individual stellar lives also provide the raw materials and energy sources that make new complexity possible, ensuring that the universe continues to evolve toward ever greater richness and diversity across cosmic time. And from these violent stellar deaths emerge some of the most exotic objects in the universe, the ultra-dense remnants of stellar cores that have been compressed beyond anything we experience in everyday life, creating strange new forms of matter that push the boundaries of physics and challenge our understanding of space, time, and gravity itself. In 1967, a graduate student named Jocelyn Bell was analyzing radio telescope data when she noticed something peculiar, a signal that pulsed with extraordinary regularity once every 1.337 seconds, more precise than any clock on Earth. At first, She and her advisor wondered if they might be detecting signals from an intelligent civilization, half-jokingly labeling the source LGM-1 for Little Green Men. What they had actually discovered was something far stranger than alien technology, a neutron star spinning 45 times per minute, sweeping beams of radio waves across space like a cosmic lighthouse. This discovery opened our eyes to one of the most extreme states of matter in the universe. Neutron stars are what remain when the core of a massive star collapses during a supernova explosion, compressed to densities so extreme that a single teaspoon of neutron star material would weigh about 6 billion tons, roughly the mass of Mount Everest, packed into a volume smaller than a sugar cube. To understand how such extreme objects form, we need to follow the final moments of stellar collapse more closely. When the iron core of a massive star can no longer support itself against gravity, it undergoes catastrophic collapse in less than a second. The core, initially about the size of Earth, shrinks to perhaps 20 kilometers in diameter while maintaining more mass than our entire Sun. The matter becomes so compressed that protons and electrons are forced together to form neutrons, creating a sphere of nuclear matter held up only by what physicists call neutron degeneracy pressure. This is matter in a state that simply doesn't exist anywhere else in the universe under normal circumstances. The density is so extreme that if you could somehow bring a piece of neutron star material to Earth, it would immediately explode with tremendous violence as the individual neutrons tried to expand back to normal atomic spacing. The entire neutron star is essentially a single atomic nucleus 20 kilometers across, containing more particles than there are cells in every human being who has ever lived. It's remarkable to think that the existence of such objects was imagined decades before they were discovered. In 1934, two astronomers sitting in California looked at the mathematics of stellar collapse and dared to suggest that stars might compress themselves into spheres of pure neutrons. At the time, it seemed like the wildest speculation, matter squeezed to such impossible densities that a sugar cube would weigh as much as a mountain. Yet there they were, quietly spinning in the cosmic dark, waiting patiently for a graduate student to notice their lighthouse signals sweeping across space. If you could journey inside a neutron star, you would find landscapes stranger than any science fiction. The outer crust might remind you of an alien city, with crystalline lattices of heavy nuclei arranged in perfect geometric patterns, stronger than any material on Earth. But venture deeper, and the very concept of individual atoms begins to break down. Nuclei merge and flow together like a thick soup of neutrons, and in the deepest core, even neutrons might dissolve into their fundamental constituents, creating a liquid of quarks that has existed nowhere else since the first moments after the Big Bang. Some neutron stars are stranger still. Magnetars carry magnetic fields so powerful they could erase the information from every credit card on Earth from halfway to the moon. Near their surfaces, magnetism becomes so intense that it begins to affect the very shape of atoms, stretching them into thin needles aligned with invisible field lines. When these magnetic monsters occasionally hiccup, releasing bursts of energy in seconds, they can briefly outshine entire galaxies and affect our planet's upper atmosphere from thousands of light years away. Ancient cultures often spoke of cosmic wheels turning in the heavens, the Hindu chakras, those spinning wheels of cosmic energy, Celtic myths of great wheels marking the seasons and the passage of cosmic time, Norse stories of giant mills grinding out the salt of the sea and the sand of beaches, Sufi mystics spinning in their ecstatic dances, believing they were mirroring the rotation that drives all creation. They couldn't have known that space really is filled with spinning stellar remnants, cosmic wheels turning with such precision that they keep better time than our finest clocks, marking cosmic rhythm with the regularity of a universal heartbeat. The lighthouse effect that makes pulsars detectable occurs because neutron stars have extremely strong magnetic fields, trillions of times stronger than Earth's magnetic field. These intense magnetic fields channel charged particles along field lines toward the magnetic poles, where they emit beams of radiation. As the neutron star spins, these beams sweep across space like the rotating beam from a lighthouse. If Earth happens to lie in the path of these beams, we detect regular pulses of radio waves, X-rays, or gamma rays as the beam sweeps past us once per rotation. The precision of pulsar timing is extraordinary. The most stable pulsars keep time more accurately than the best atomic clocks, with their rotation rates changing by less than 1 part in a billion over years of observation. This clock-like precision arises because neutron stars are incredibly rigid objects. Their crusts are made of crystalline nuclear matter that's about 10 billion times stronger than steel. When a neutron star spins, it maintains that rotation with almost no friction or resistance to slow it down. Some pulsars spin hundreds of times per second, rotating so fast that their equators move at significant fractions of the speed of light. These millisecond pulsars are thought to be old neutron stars that have been spun up by accreting matter from a companion star, like cosmic tops that have been given a powerful new twist. The fastest known pulsar, PSRJ 1748-244 SIXAD, spins 716 times per second, so fast that a point on its equator is moving at about 25% the speed of light. The discovery of pulsars provided the first indirect evidence for gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. When two neutron stars orbit each other closely, they gradually spiral inward as they lose energy to gravitational radiation. The Hulse-Taylor binary pulsar, discovered in 1974, showed exactly this behavior, with the orbital period decreasing at precisely the rate predicted by Einstein's equations. This observation earned the 2017 Nobel Prize in Physics and confirmed that massive accelerating objects really do create waves in the fabric of space-time itself. But not all stellar cores that collapse become neutron stars. If the core is too massive, more than about 3 times the mass of our Sun, even neutron degeneracy pressure cannot halt the collapse. In these cases, gravity wins completely, and the core continues shrinking until it becomes what we call a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. The idea of darkness so complete that light itself cannot escape has haunted human imagination for centuries. Long before we understood the physics of curved space-time, an English clergyman named John Michell sat by candlelight in 1783 and calculated that if you could compress enough matter into a small enough space, not even light could break free from its gravitational embrace. He called them dark stars, these hypothetical objects that would be invisible against the night sky. He couldn't have imagined that such objects actually exist, scattered throughout the galaxy like invisible holes cut out of the fabric of space itself. Einstein's equations, scribbled on a German physicist's notepad during the First World War, revealed that massive objects don't just pull on things, they actually bend and warp the fabric of space-time like a heavy ball pressing down on a stretched rubber sheet. Karl Schwarzschild, working out the mathematics while serving on the Russian front, calculated exactly how much space-time would curve around a perfectly round mass. Tragically, He died of disease just months after making this contribution to our understanding of cosmic geometry, never knowing that his equations described some of the strangest objects in the universe. The boundary around a black hole where escape becomes impossible is called the event horizon, a name that captures something poetic about these cosmic mysteries. It's the place where events simply stop being visible from the outside universe, where information disappears beyond our ability to retrieve it. For a black hole with the mass of our Sun, this invisible boundary would be about 6 kilometers from the center, smaller than most earthly cities, yet marking the edge of a region where space and time themselves become so distorted that our intuitive understanding of reality breaks down. Human cultures have long been drawn to concepts of ultimate voids, regions where normal existence gives way to something beyond comprehension. Ancient Babylon spoke of Tiamat, the primordial chaos that existed before creation brought order to the cosmos. Hindu philosophy describes cosmic dissolution, when all of manifest reality dissolves back into undifferentiated potential. Buddhist thought explores shunyata, the emptiness that underlies all apparent form. Aboriginal Dreamtime stories tell of void places where the usual rules don't apply, where ancestral beings could step outside the normal flow of time and space. These weren't scientific predictions, but they show how deeply the human mind is drawn to contemplate regions of ultimate mystery, places where the familiar world gives way to something unimaginable. For decades, black holes remained mathematical curiosities, so extreme that even Einstein doubted they could actually exist. It seemed impossible that nature would permit such cosmic monsters. But the universe, as it turns out, is far stranger and more wonderful than our most daring imaginings. Black holes are real, and they hide throughout the galaxy, detectable only through their gravitational effects on nearby stars and gas. Finding an invisible object in the vastness of space requires considerable cleverness. Astronomers learn to look for the signatures of violence, streams of superheated gas spiraling inward at tremendous speeds, glowing brilliantly just before disappearing forever past the event horizon. When a black hole has a companion star, it can strip material away like a cosmic vampire, creating swirling disks of matter that shine in X-rays as they heat up during their final plunge into darkness. In 2019, an international team of astronomers managed something that seemed almost impossible. They photographed the shadow of a black hole, using radio telescopes scattered across the entire Earth, working together like segments of a single planet-sized eye. They captured the dark silhouette of the supermassive black hole at the center of the galaxy M87. There it was, exactly as Einstein's century-old equations had predicted, a perfect dark circle surrounded by a glowing ring of doomed matter, spinning and heating as it spiraled toward the point of no return. Black holes represent the ultimate victory of gravity over all other forces. Once matter crosses the event horizon, it can never escape or send any information back to the outside universe. From the perspective of a distant observer, objects falling toward a black hole would appear to slow down and freeze at the event horizon, their light becoming increasingly red-shifted until it fades from view. But from the perspective of the falling object, the journey would continue normally until reaching the singularity at the center. The distortion of space-time around black holes creates effects that seem almost magical. Time itself runs slower in strong gravitational fields, an effect called gravitational time dilation. Near a black hole, this effect becomes extreme. A process that takes 1 hour near the event horizon might correspond to years of time passing for observers far from the black hole. This means that black holes are not just regions of extreme gravity, but also regions where time itself behaves in strange and counterintuitive ways. Despite their reputation as cosmic vacuum cleaners that devour everything in their path, black holes only affect objects that venture very close to them. If our Sun were somehow replaced by a black hole of equal mass, Earth would continue orbiting normally. The gravitational pull at our distance would be exactly the same. Black holes only become dangerous when you approach within a few times the radius of the event horizon, where the difference in gravitational pull between your head and feet becomes sufficient to stretch you apart in a process that physicists cheerfully call spaghettification. Some black holes grow to truly enormous sizes by continuously accreting matter from their surroundings. Supermassive black holes containing millions or billions of times the mass of our Sun lurk at the centers of most large galaxies. These cosmic giants create some of the most energetic phenomena in the universe when matter falls toward them. The infalling material forms a swirling accretion disk that heats up to millions of degrees, glowing brilliantly across the electromagnetic spectrum and sometimes launching jets of high-energy particles thousands of light years into space. The recent development of gravitational wave detectors has opened an entirely new window into the universe of neutron stars and black holes. When two neutron stars spiral together and merge, they create ripples in space-time that can be detected by instruments like LIGO and Virgo. These gravitational wave signals provide information about the masses, spins, and internal structure of neutron stars that we could never obtain through traditional telescopes. The first detected neutron star merger, observed in August 2017, was simultaneously detected in gravitational waves and across the electromagnetic spectrum from gamma rays to radio waves. This event, dubbed a kilonova, created conditions extreme enough to forge heavy elements like gold and platinum through rapid neutron capture processes. The collision of two neutron stars, each containing more mass than our Sun, compressed into a sphere the size of a city, released more energy in gravitational waves alone than all the stars in the observable universe emit in light. Modern indigenous cultures have sometimes incorporated pulsar discoveries into their traditional storytelling frameworks. Some Maori astronomers have drawn parallels between the regular pulsing of pulsars and the traditional concept of cosmic heartbeats that maintain the rhythm of universal time. These contemporary interpretations show how ancient wisdom about cosmic rhythms can find new expression through modern astronomical discoveries. The study of neutron stars and black holes pushes the boundaries of human understanding in profound ways. These objects exist in regimes where the familiar laws of physics are stretched to their limits, where matter behaves in ways that have no analogue in everyday experience, and where space and time themselves become malleable. They serve as natural laboratories for testing our most fundamental theories about the nature of reality. Yet for all their exotic properties, neutron stars and black holes play crucial roles in the cosmic ecosystem. Neutron star mergers help distribute heavy elements throughout the universe. Black holes regulate star formation in galaxies through their energetic outflows. Pulsars serve as cosmic beacons that help us map the structure of our galaxy and test fundamental physics in extreme environments. The lighthouse beams from pulsars sweep across the galaxy with mechanical precision, marking cosmic time with an accuracy that exceeds our best earthly clocks. In their regular pulses we hear the heartbeat of stellar remnants so dense that a city-sized sphere contains more mass than our Sun. These cosmic lighthouses remind us that even in death stars continue to illuminate the universe, though now in forms so exotic that they challenge our understanding of matter, energy, space, and time itself. As we contemplate these dense stellar corpses spinning in the cosmic dark, sending out their regular signals across vast distances of space and time, we begin to see how stellar death becomes part of an even grander cycle. The heavy elements forged in stellar cores and scattered by supernova explosions, the shock waves that compress interstellar gas clouds, the neutron stars that enrich space with their exotic matter. All of these contribute to the ongoing story of cosmic evolution, the endless cycle of stellar birth, death and rebirth that has been shaping the universe for over 13 billion years. Stand outside on a clear night and look up at the constellation Orion. Those bright stars marking the hunter's shoulders and belt seem eternal and unchanging, fixed points of light that have guided human navigation and storytelling for millennia. But if you could watch that same patch of sky across cosmic time, speeding up millions of years into seconds, you would witness an endless dance of stellar birth and death, with new stars igniting as old ones fade away, the whole constellation slowly shifting and changing as each stellar generation enriches the space around it with the ashes of nuclear burning. This is the cosmic cycle that has been running since the first stars ignited in the early universe, a vast recycling system where stellar death becomes the seed of stellar birth, where the end of one story becomes the beginning of countless others. Every atom in your body, except for the simplest hydrogen, has participated in this cycle multiple times, forged in ancient stellar cores, scattered by supernovae, gathered into new star systems, and eventually incorporated into the rocky planet we call home. When the universe was young, perhaps only a few 100 million years after the Big Bang, the first generation of stars began to shine. These primordial giants were made almost entirely of hydrogen and helium, the only elements that existed in significant quantities from the universe's earliest moments. They were massive, luminous, and short-lived, burning through their nuclear fuel in just a few million years before ending their lives in spectacular supernova explosions. Imagine witnessing the universe in those early epochs, when the first starlight began to pierce the cosmic dark. The sky would have been filled with brilliant blue giants, each one a nuclear furnace burning with the intensity of millions of suns. These population 3 stars, as astronomers call them, were unlike any stars we see today. Pure and simple in their composition, yet magnificent in their power. They lived fast and died young, their brief existences marking the end of the universe's dark age and the beginning of cosmic chemistry. But these first stellar deaths were profoundly important because they seeded space with the first heavy elements. The carbon, oxygen, silicon and iron created in their cores and scattered by their explosive ends mixed with the pristine hydrogen and helium of the early universe, creating a slightly enriched medium from which the next generation of stars could form. This second generation inherited the nuclear legacy of the first, and when they too lived and died, they added their own contributions to the growing inventory of heavy elements. Each successive generation built upon the achievements of the previous one, like a cosmic relay race where each runner passes along not just a baton, but an increasingly complex collection of atomic building blocks. The third generation of stars, born from gas clouds enriched by 2 previous cycles of stellar evolution, could form smaller, longer-lived stars surrounded by disks of dust containing the rocky materials needed for planet formation. Our own Sun belongs to this third generation, a stellar heir to billions of years of cosmic enrichment. Ancient creation myths often spoke of cycles within cycles, of cosmic seasons that repeated on scales far larger than earthly time. The Hindu concept of cosmic days and nights, each lasting billions of years, during which the universe would manifest and then dissolve back into potential before beginning again. The Mayan understanding of nested time cycles, where smaller periods fit within larger ones, like wheels within wheels, Aboriginal Dreamtime stories that describe the continuous creation and recreation of the world through the actions of ancestral beings. These cultures intuited something profound about cosmic time, that creation is not a single event but an ongoing process of renewal and transformation. Modern astronomy has revealed that this intuitive understanding was remarkably accurate. The universe really does operate in cycles of stellar birth, life and death that play out across timescales so vast they dwarf human history. Each stellar generation builds upon the achievements of the previous one, slowly enriching the cosmic environment with the materials needed for complexity, chemistry, and eventually life. The process begins in the cold depths of space, in the vast molecular clouds that drift between the stars like cosmic fog. These nebulae are not empty. They contain the accumulated debris from countless stellar deaths, mixed with the primordial hydrogen that has existed since the early universe. The gas is thin beyond imagining, often containing only a few hundred atoms per cubic centimetre, but it's rich in the heavy elements that previous generations of stars have contributed to the cosmic inventory. These molecular clouds are vast beyond human comprehension. Some stretch across hundreds of light years, containing enough material to form thousands of new stars. If you could somehow travel through one, you would find yourself in a realm of icy silence, where temperatures hover just a few degrees above absolute zero, and the only light comes from distant stars filtered through veils of dust. Here, in this cosmic winter, the complex chemistry of star formation slowly unfolds across millions of years. Within these clouds, the patient force of gravity slowly gathers material together. A slight density enhancement, perhaps triggered by the shock wave from a nearby supernova, or the gravitational influence of a passing star, becomes the seed around which new stellar formation begins. As the gas cloud contracts, it fragments into smaller condensations, each destined to become a new star system. It's a process so gradual that even across human lifetimes, the clouds appear virtually unchanged. Yet over cosmic time, they're dynamic nurseries of stellar creation. The heavy elements scattered by previous stellar generations don't just participate passively in this process, they fundamentally transform it. Dust grains made of carbon, silicon, and other heavy elements serve as catalysts for chemical reactions and as surfaces where hydrogen molecules can form. These dust particles also help cool the contracting gas by radiating away heat, allowing smaller, cooler condensations to form stable stars. In the earliest universe, when heavy elements were scarce, only the most massive stars could form. But billions of years of cosmic enrichment have made possible the full spectrum of stellar masses we see today. But here's where the cosmic cycle reveals its elegant interconnectedness. The heavy elements mixed into the contracting gas cloud fundamentally change the star formation process. Pure hydrogen and helium gas can only cool and contract through certain mechanisms, but gas enriched with heavier elements can radiate energy away more efficiently, allowing smaller, cooler condensations to form stable stars. Without the carbon, oxygen, and other elements contributed by previous stellar generations, stars like our Sun could never have formed. The enrichment process is beautifully uneven across the galaxy. Regions near the galactic center, where stars have been forming and dying for over 12 billion years, show higher concentrations of heavy elements than the outer spiral arms, where stellar recycling has had less time to operate. Our solar system formed in a middle region of the galaxy inheriting just the right mix of heavy elements to create a rich diversity of rocky and gaseous worlds. Had we formed in the galactic centre, the abundance of heavy elements might have led to the formation of numerous massive rocky planets with crushing gravitational fields. Had we formed in the outer regions, the scarcity of heavy elements might have prevented the formation of substantial rocky planets at all. The debris from stellar death does more than enable new star formation. It provides the raw materials from which planetary systems can condense. When our solar system formed 4.6 billion years ago, the disk of gas and dust surrounding the young sun contained silicon, iron, magnesium, and other rocky materials that had been forged in the cores of massive stars and scattered by ancient supernovae. These elements condensed into the small grains that eventually accumulated into asteroids, and asteroids collided and merged to form the rocky planets, including Earth. In this way, stellar death directly enables the formation of worlds like ours. The iron in Earth's core, the silicon in its rocks, the oxygen in its oceans, all of these materials trace their origins back to nuclear fusion reactions that took place in stellar cores billions of years ago. Our planet is quite literally built from the recycled remains of ancient stars, a testament to the cosmic recycling that links stellar evolution to planetary formation. The cycle operates on multiple timescales simultaneously. Individual massive stars live and die in just a few million years, quickly returning their processed material to the interstellar medium. Lower mass stars like our Sun burn for billions of years before gently puffing off their outer layers as planetary nebulae, slowly enriching nearby space with the products of their long nuclear burning. The most massive stars explode as supernova, instantly distributing their heavy elements across vast regions of space and triggering new rounds of star formation through their violent shock waves. Celtic traditions spoke of the cauldron of rebirth, a mystical vessel where death transformed into new life. Norse mythology described the world tree Yggdrasil, whose roots and branches connected different realms of existence in an endless cycle of growth, death, and renewal. These metaphors capture something essential about how the universe actually works. Stellar death is not an ending, but a transformation, a way of ensuring that the materials of complexity can spread throughout the cosmos and participate in ever more elaborate forms of organization. The enrichment process has been gradual but persistent. The early universe contained virtually no elements heavier than lithium, but billions of years of stellar evolution have steadily increased the abundance of carbon, oxygen, silicon, iron, and other materials essential for rocky planets and complex chemistry. Astronomers can trace this chemical evolution by studying stars of different ages. Older stars show the signatures of fewer heavy elements, while younger stars reveal the cumulative effects of billions of years of stellar nucleosynthesis. Our own solar system represents the current state of this cosmic enrichment process. The Sun formed from a molecular cloud that had been enriched by hundreds of previous stellar generations, giving it enough heavy elements to support the formation of rocky planets with solid surfaces, liquid oceans, and complex geology. Without this inheritance from previous stellar cycles, Earth would never have formed, and the chemistry that makes life possible would never have developed. But the cosmic cycle doesn't stop with planetary formation. Life itself becomes part of the larger recycling process, taking up heavy elements from the environment and incorporating them into increasingly complex molecules and structures. The carbon in DNA, the phosphorus in cell membranes, the trace metals in enzymes, all of these biological materials ultimately derive from stellar nucleosynthesis, carrying the nuclear legacy of ancient stars into the realm of living systems. When you breathe, you're participating in this cosmic recycling on the most intimate level. The oxygen molecules entering your lungs were forged in the cores of massive stars that lived and died billions of years ago. The carbon atoms in your body have likely passed through multiple stellar generations, perhaps spending millions of years locked in the heart of a red giant before being returned to space through stellar winds, then drifting through interstellar clouds, before eventually becoming incorporated into the organic molecules that make up living tissue. This personal connection to stellar cycles extends to every aspect of your existence. The calcium in your bones was created when silicon nuclei fused in a stellar core under temperatures of hundreds of millions of degrees. The iron in your blood carries the signature of nuclear reactions that took place in the final moments before a massive star's collapse. Even the sodium and potassium that help carry nerve signals through your brain bear the nuclear fingerprints of ancient stellar alchemy. There's something deeply moving about tracing these atomic biographies back to their stellar origins. The phosphorus in your DNA has travelled an unimaginable journey, forged in the heart of a dying star, blasted into space by a supernova explosion, drifting through the cosmic medium for millions of years, eventually incorporated into the molecular cloud that gave birth to our solar system, condensed into rocky planetesimals, delivered to Earth perhaps by asteroids or comets, taken up by primitive life forms, and finally organized into the complex molecular machinery that stores your genetic information. In this sense, you are not just made of star stuff. You are star stuff that has been processed through the entire history of cosmic evolution, carrying within your body the accumulated achievements of billions of years of stellar nucleosynthesis. Your existence represents the universe's capacity to organize its stellar products into increasingly complex forms, culminating in structures capable of consciousness and self-reflection. The cycle continues even now, all around us. In the Orion Nebula, new stars are condensing from gas clouds enriched by previous stellar generations. They're forming planetary disks containing the heavy elements needed for rocky world formation. In distant galaxies, supernovae are scattering fresh batches of heavy elements into space, providing the raw materials for future stellar and planetary systems. The cosmic recycling that created our solar system is still operating, still transforming stellar death into stellar birth across the observable universe. But the cycle operates at different rates in different environments. In elliptical galaxies, where most of the star formation occurred billions of years ago, the recycling has largely ceased. These stellar populations are aging gracefully, with few new stars being born to carry forward the cycle of enrichment. In contrast, irregular galaxies and the spiral arms of disk galaxies like our own Milky Way continue to form new stars at steady rates, ensuring that the cosmic cycle continues to operate and evolve. Our own galaxy provides a perfect example of how this recycling shapes galactic evolution. The Milky Way's central bulge contains old, metal-rich stars that form from gas already enriched by previous stellar generations. The disk contains a mix of old and young stars, with the youngest found primarily in the spiral arms, where ongoing star formation continues to process gas through stellar cores. The galactic halo contains the oldest, most metal-poor stars, fossils from the early epochs when heavy element abundance was much lower throughout the galaxy. This galactic archaeology allows us to trace the history of cosmic enrichment in our own stellar neighborhood. By studying stars of different ages and compositions, astronomers can reconstruct how the abundance of heavy elements has increased over the Milky Way's 12 billion year history. It's like reading the galaxy's chemical evolution in the spectra of its stellar inhabitants. each star carrying the signature of the cosmic recycling that made its formation possible. There's something profoundly hopeful about this cosmic perspective. Individual stars may live and die, but their contributions become part of an ongoing story that stretches across cosmic time. The death of massive stars 10 billion years ago helped make possible the formation of our Sun and the rocky planets that orbit it. Our Sun's eventual death, billions of years in the future, will contribute materials and energy to stellar systems that have not yet formed, perhaps providing the heavy elements that will make possible new forms of complexity we can't yet imagine. Ancient Taoist philosophy spoke of the eternal transformation of all things, the way endings become beginnings in an endless flow of change. Modern astrophysics has revealed that this philosophical insight describes a literal truth about cosmic evolution. Stellar endings really do become stellar beginnings in a grand cycle that has been operating since the first stars ignited and will continue long after our own Sun has faded to a white dwarf. The cosmic cycle also operates on scales larger than individual stars. Galaxies themselves evolve through cycles of star formation and stellar death. Their spiral arms mark in regions where shockwaves from supernovae compress gas clouds and trigger new rounds of stellar birth. The Milky Way has been recycling stellar material for over 12 billion years, its current generation of stars inheriting the nuclear legacy of countless previous generations. Even the space between galaxies participates in this recycling. Galactic winds driven by supernova explosions can carry enriched material far beyond a galaxy's boundaries, seeding the intergalactic medium with heavy elements that may eventually be incorporated into new galactic systems. In this way, the cosmic cycle operates on the largest scales of space and time, linking the evolution of individual stars to the chemical enrichment of the entire universe. As we stand beneath the night sky and contemplate this vast recycling system, we begin to understand our place within cosmic history. We are not separate from the stars. We are made of stellar material, animated by stellar energy, participating in the same cosmic cycle that has been shaping the universe for over 13 billion years. Every element in our bodies carries the signature of ancient nuclear burning, connecting us directly to the heart of stars that died before our solar system was born. The cycle that created us continues even now, ensuring that the story of cosmic evolution will outlast any individual star, planet, or form of life. Stellar death feeds stellar birth, which enables planetary formation, which makes possible the complex chemistry from which life emerges. And life, in turn, contemplates the cosmos and comes to understand its own stellar origins, closing a loop of matter and meaning that stretches from the nuclear fires of stellar cores to the neural networks of conscious brains. This is perhaps the most beautiful aspect of the cosmic cycle, that it eventually produces observers capable of understanding it, beings made of star stuff who can look up at the night sky and recognize their kinship with the distant lights. In contemplating stellar evolution, we are the universe becoming aware of its own creative processes, the cosmic cycle achieving a kind of self-reflection through the consciousness it has made possible. And with that thought of cosmic self-awareness emerging from stellar cycles, we come to the end of our journey through stellar life and death, but also to a new beginning, an understanding of how we fit into the vast story of cosmic evolution, and how the death of stars billions of years ago made possible not just our existence, but our ability to comprehend and appreciate the beautiful cycles that connect us to the farthest reaches of space and time. Tonight, when you step outside and look up at the stars, you'll be seeing them with different eyes than when we began this journey together. Those distant points of light are no longer just decorations scattered across the darkness. They're nuclear furnaces at every stage of their cosmic lives, each one carrying out the patient work of transforming simple elements into complex ones, converting hydrogen into the building blocks of worlds and life. That bright star near the horizon might be a young giant, recently ignited and beginning its billions of years of steady hydrogen burning. The reddish point of light in another constellation could be an aging star in its giant phase, swelling and pulsing as it nears the end of its nuclear lifetime. Somewhere among those countless distant suns, massive stars are at this very moment undergoing the final collapse that will transform them into supernovae, their explosions already racing toward us at the speed of light, though they won't reach Earth for thousands of years. You've become part of an ancient human tradition, looking up at the night sky and recognizing patterns, meaning, and connection. But your understanding now reaches deeper than the constellation stories told around campfires for millennia. You know that the light entering your eyes carries information about nuclear processes happening in stellar cores, that the colors and brightness of stars reveal their temperatures, masses, and evolutionary states. You've learned to read the sky as a vast library written in starlight, each point of light a chapter in the ongoing story of cosmic evolution. The timescales we've explored together dwarf human experience in ways that can be difficult to fully grasp. When we speak of stellar lifetimes measured in billions of years, we're describing periods so vast that entire species evolve and go extinct while a single star burns steadily in the cosmic background. Mountains rise and erode to dust. Continents drift across planetary surfaces, and ice ages come and go while stars continue their patient work of nuclear fusion, largely unchanged across these immense spans of time. Yet you are intimately connected to this stellar story in ways both profound and personal. The calcium strengthening your bones was forged when silicon nuclei collided in a stellar core at temperatures exceeding 600 million degrees. The iron carrying oxygen through your bloodstream bears the nuclear signature of a massive star's final moments before collapse. The oxygen you're breathing as you read these words was created when helium nuclei fused together in the heart of a red giant star, then expelled into space when stellar winds carried away the star's outer layers. This connection runs deeper than just the material elements of your body. The energy that powers your thoughts, the warmth that maintains your body temperature, the light that allows you to see, all of these trace their ultimate origins back to nuclear fusion in stellar cores. Our Sun is a typical main sequence star, converting hydrogen to helium through the same processes that have been lighting up the universe for over 13 billion years. The sunlight warming your skin began its journey as fusion reactions in the solar core, then spent thousands of years working its way to the surface before racing across 150 million kilometers of space to reach you. Even the fundamental forces and processes that govern your existence operate according to the same physical laws that determine stellar evolution. The electromagnetic force that holds atoms together in your DNA is the same force that prevents stellar cores from collapsing under their own gravity. The strong nuclear force that binds protons and neutrons in atomic nuclei is what powers the fusion reactions that make stars shine. In studying stellar physics, we've been exploring the same fundamental principles that govern the chemistry and biology of life itself. There's something deeply humbling about this cosmic perspective. Your daily concerns, your personal struggles, your hopes and dreams, all of these unfold against the backdrop of stellar cycles that operate across timescales so vast they make human history seem like a brief flicker. Yet there's also something profoundly empowering about recognizing your place in this larger story. You are not separate from the universe. You are the universe becoming aware of itself, cosmic material organized into a form capable of consciousness and wonder. This capacity for wonder is itself remarkable when viewed from a cosmic perspective. The same stellar processes that created the heavy elements in your body also made possible the complex chemistry of neural networks, the intricate molecular machinery that allows matter to become aware of its own origins. In developing consciousness, the universe has created a way of examining itself from the inside, of understanding its own creative processes, through the minds that stellar evolution has made possible. Ancient cultures intuited aspects of this connection through their mythologies and spiritual practices. When they spoke of humans being made from clay or earth breathed upon by gods, they were recognizing our material kinship with the planetary environment. When they described cosmic cycles of creation and destruction, they were sensing the deep rhythms of stellar evolution that actually govern cosmic change. When they looked up at the stars and saw ancestors or spirits, they were intuiting a connection that modern astrophysics has shown to be literally true. We really are made of stellar material, linked by unbroken chains of causation to the nuclear fires burning in distant suns. The scientific understanding we've developed adds new dimensions to these ancient insights without diminishing their power. Knowing that stellar nucleosynthesis created the elements of life doesn't make existence less meaningful. It reveals meaning at cosmic scales, showing how your existence participates in the universe's ongoing experiment with complexity and consciousness. You are not just accidentally here, you are the current expression of 13.8 billion years of cosmic evolution, the temporary organization of stellar products into a form capable of contemplating its own origins. This perspective can transform how you relate to the natural world around you. The rocks beneath your feet contain minerals forged in ancient stellar cores. The water you drink carries hydrogen nuclei that have existed since the early universe, mixed with oxygen created in stellar furnaces. The air you breathe is part of an atmosphere whose composition has been shaped by billions of years of stellar recycling, volcanic outgassing, and biological processes, all ultimately dependent on the steady energy output of our local star. Even human culture and technology represent extensions of cosmic evolution. When you use tools, create art, or engage in scientific research, you're participating in the universe's tendency toward increasing complexity and organization. The same processes that led from simple hydrogen and helium to heavy elements, from stellar deaths to planetary formation, from chemistry to biology, have also led to consciousness, culture, and the capacity for cosmic understanding. Looking toward the future, stellar evolution provides a framework for thinking about cosmic destiny across timescales that dwarf human planning. Our Sun will continue its steady hydrogen burning for about another 5 billion years, gradually brightening as its core composition changes, eventually entering its red giant phase and fundamentally altering conditions in the solar system. Long before that happens, other massive stars in our galactic neighborhood will live out their complete life cycles, enriching the interstellar medium with fresh batches of heavy elements and triggering new rounds of star formation through their supernova explosions. The cosmic recycling we've explored will continue operating for trillions of years into the future, long after the last massive stars have exhausted their fuel and faded to white dwarfs or collapsed into black holes. The universe will gradually grow dimmer and cooler as stellar formation rates decline and existing stars burn through their nuclear reserves. But this far future cooling represents not an end, but another phase in cosmic evolution, one where new forms of complexity might emerge under conditions we can barely imagine. Your awareness of these vast timescales and cosmic processes doesn't diminish the importance of human-scale experiences. It enriches them by providing context and connection. The love you feel for family and friends operates through neural chemistry, made possible by stellar nucleosynthesis. The beauty you perceive in art or nature reflects your participation in a universe that has evolved the capacity for aesthetic appreciation. Your ethical concerns about justice, meaning, and purpose represent the cosmos developing moral awareness through conscious beings like yourself. Tonight, as you settle into sleep, remember that the entire stellar story we've explored together continues unfolding around you. In stellar nurseries scattered throughout the galaxy, new stars are condensing from gas clouds enriched by previous stellar generations. In the cores of red giants, helium nuclei are fusing to create carbon and oxygen. In the hearts of massive stars approaching supernova, silicon is burning to create iron and the other heavy elements that make rocky planets possible. All of this cosmic activity proceeds according to physical laws, so fundamental and reliable that you can predict stellar behavior across billions of years and billions of light years with remarkable accuracy. Yet within this cosmic regularity, there's endless room for novelty, complexity, and surprise. Each stellar system is unique. Each planetary environment creates its own possibilities. Each conscious being brings its own perspective to the cosmic story. You are both a product of stellar evolution and a participant in it. The elements in your body will eventually be returned to the cosmic recycling system, perhaps to become part of future stars, planets, and forms of life we can't yet imagine. Your thoughts and experiences, while temporary on cosmic timescales, represent genuine achievements in the universe's exploration of its own potential for awareness and meaning. So when you look up at the stars tonight, remember that you're not just observing the universe from the outside, you're experiencing it from within, as one of the countless ways cosmic evolution has learned to contemplate itself. In your wonder at the stellar cycles of birth, life, death, and rebirth, the universe achieves a moment of self-recognition, seeing its own beauty reflected in the consciousness that stellar evolution has made possible. Rest well, knowing that you carry within yourself the achievements of billions of years of cosmic creativity, and that your existence adds something unique and irreplaceable to the ongoing story of stellar evolution that connects every atom in your body to the nuclear fires burning in the distant stars. Sweet dreams, fellow travelers through space and time. May your rest be peaceful, your wonder undimmed, and your curiosity about the cosmos continue to connect you to the greatest adventure in human history, our ongoing journey to understand the universe and our place within it. Clear skies and boundless wonder, the sleepy astronomer.